Going through everything topic by topic, I've decided how about we just go through everything at once, and I'll just simply timestamp the subtopics in the comment section below. So without further ado, let's have a quick look at the syllabus content and get right into it. So the first thing we're going to be looking at is naming organic compounds, and this section will make a lot more sense once you sort of understand the individual subtopics with alkanes, alkenes, alcohols, carboxylic acids, and esters. So it might be advisable that you just sort of listen to what I'm saying now and come back to this section after you've covered the rest of the video. But the main idea is that organic chemistry, in organic chemistry you find sort of substances that have certain functional groups, and functional groups are basically groups of atoms responsible for the characteristic reactions of a particular compound. And so for the most part, organic chemistry, you're just dealing with sort of carbon chains, right? So let's just screenshot this for a moment. For the most part, you're just dealing with sort of carbon chains of a certain length with certain functional groups attached. For example, if you take a look at the alcohol over here, the functional group that you find is the OH group attached to the carbon. So if you find that you have a carbon chain with an OH group attached, you instantly know that this is the alcohol functional group. And this functional group, which is again the group of atoms that is responsible for the characteristic reactions of the alcohols, basically, then you know that this compound is an alcohol. And so why I'm talking about this is because you really do need to be able to immediately figure out or be familiar with the functional groups, and we will go through each of these individually throughout the video. But the functional group of a compound basically dictates most of the name. Each of these functional groups have a specific name attached to it. So if you have an alkane, which has the functional group of just a carbon attached to a carbon with a single bond, then it'll end with the name ane. An alkene that has a functional group of carbon-carbon double bond will end with the name ene. An alcohol, as we've described before, will have the functional group OH, and that will end with the name anol. The carboxylic acids end with something anoic acid, and they have the functional group of a carbon attached to an oxygen with a double bond, and towards that carbon as well there's an OH group attached as well. So these are the functional groups that you need to know, but again, we will be covering them individually. Esters are a fairly unique case. It's basically when a carboxylic acid reacts with an alcohol, and we will dig into this in a bit more detail later. So basically, naming an organic compound comes into 3 easy steps, except for the esters. Esters are unique, but for the most part, you can do it in 3 steps, right? You've got, the first step is to find the suffix, which is the end part of the name, and as we described before, this is dictated by the functional group of the organic compound. Then you need to find the prefix, which is simply the front part of the name, and that's dictated by the number of carbon atoms in the longest chain of the molecule. Generally in IGCSE, you're going to be only looking at a single chain. They're not going to give you branches and things like that, so it's going to be pretty easy. And the third step is to find the position of the functional group, because that matters as well. But it's the third step here isn't exactly relevant for your course, because generally they're not going to ask about it, but I think it's just good to be aware anyway. And so I think the easiest way to do this is just to take a look at this molecule here, and give you an example. So if you take a look at this molecule, right, as I said before, this is the OH functional group. So we immediately know that because it has the OH functional group, it is an alcohol. And if you take a look at these bullet points here, over here, you can see that alcohols will always end with the name anol. So it's going to be something anol. But what is the front part of the name? And that's where the prefix comes in. You take a look at the number of carbon atoms, and so 1 carbon atom is meth, 2 carbon atom is eth, 3 carbon atoms is prop, and so on. And so if you take a look here, if you count the number of carbon atoms inside the chain of this molecule, you have 1, you have 2, you have 3, and therefore it's prop, as you see on the table here towards the right. So propanol is the name of this organic compound. Now, the last step 3 is to find the position of the functional group, and this is quite important because if you take a look at these two molecules here, the left and the right, they are very, very similar molecules, but if you can spot the difference, the only difference is the functional group in the first molecule is attached to the third carbon, and in this molecule here on the right, the functional group is actually attached to the second carbon. Now, how you number the carbon is actually really important. You know how I just said that the OH functional group is attached to the third carbon? This is in fact quite wrong, because if you actually think about it, you can also equally argue that it's attached to the first carbon, because if you read from right to left, it's 1, 2, and 3. And we're always going to assume that the functional group is attached to the lowest number carbon, and we're going to start the chain from there, or at least counting the chain from there. So instead of going 1, 2, 3 and saying that the functional group is attached to the third carbon, instead, when that's a wrong assumption, because in organic chemistry, as I said, we're going to attach it to the lowest number carbon, so not 3 and 1 in this case, and we're going to count the chain going that way there. So this last carbon would become the third carbon instead. And so you would actually dictate or denote that this is attached to the first carbon by writing 1 propanol, and the number at the front suggests that it is attached to the first carbon. Now, if you take a look at the second carbon, because despite the fact that they have equal amount of molecules in them, they are structurally different, because again, the hydroxyl group or the alcohol group or the functional group here is actually attached to a different carbon as opposed to the first one, and we call these structural isomers, which are basically molecules that have the same molecular formula, and so it's got the same amount of molecules inside them, but they're structurally different. And so you would denote this isomer as 2-propanol. But again, I don't really think the numbers are so much important for your course. Generally, they will sort of add the functional groups towards the end of the molecule, and so you can sort of ignore the number if it's attached to the first carbon, like so. But I think it's just important for you to know that indeed in the real world, the position of the functional group matters, and they will start to get picky about that after IGCSE when you get to A levels. But either way, most of what you'll be dealing with will be simple organic compounds, so the first 2 steps are of the most importance there. So it really is just about you being able to recognize functional groups and knowing what makes an alkane, alkene, alcohol, and you will develop this skill as we move throughout the video, and naming the compounds should be pretty easy after that. So the topic of fuels is not a really big one. There are 3 main fuels that you need to be familiar with. You've got coal, you've got natural gas, and petroleum. But most of what they'll ask you in exams would be the idea that fractional distillation can separate petroleum into more useful mixtures of hydrocarbons, and hydrocarbons are molecules that only contain carbon and hydrogen, and we call these fractions. So if you take a look at petroleum here, you can actually gain a lot of different fractions like residue, fuel oil, heating oil, diesel, paraffin, and petrol, and each of these have different uses. Petrol can be used in cars, paraffin can be used for aircraft fuel, diesel can be used for fuels for cars, lorries, and buses, heating oil can be used for fuel for central heating, fuel oil can be used as fuel for ships and power stations, and residue can be used for roads and roofs and bitumen. But there isn't exactly a lot of explaining to do here. It's just for you to be aware of the names of the different fractions and their individual uses. So homologous series is a series of compounds with the same functional group. We took a look at functional groups before. We've got the alcohol functional group that has the OH group attached to the organic compound. We have various functional groups, and the main ones would be alkenes, alkanes, alcohols, and carboxylic acids, and each of these have unique sort of groups of molecules that sort of define the functional group. But homologous series are molecules with the same functional group, but the main differences are that they have different carbon numbers, the different total number of carbons inside the structure, or at least in the chain. So the characteristics of homologous series would be that all members of the series can be represented by the same general formula, which is just basically a formula that tells you if you have a certain amount of carbons, then how much hydrogens you'd have in that particular molecule. So consecutive members of the series will differ by 1 carbon and 2 hydrogens, and they'll all share sort of similar chemical properties because, again, I said functional groups dictate the chemical properties of the compounds, and every member of the homologous series will have that particular functional group, so you can expect the chemical properties to be similar. The physical properties along the series will actually also change in a fairly predictable way as well. So this is an example of the homologous series of alkanes. Now alkanes, the functional group, I mean really technically speaking, alkanes are lacking in functional group, but for the sake of your course, the functional group can be said to be the carbon-carbon single bond. So alkanes are hydrocarbons that only have carbon-carbon single bonds, and the carbons are attached to hydrogens with single bonds as well. So if you have a molecule that only has carbon and hydrogens and you only see single bonds in them, then you know that it's an alkane. And so if you take a look at the homologous series of alkanes, each of them have the same functional group. You can see that from number 1 to number 5 and beyond, all of them will basically have the same functional group of carbon-carbon single bonds only. And so the idea is that the first member of the series will have 1 carbon, the second member will have 2 carbons, and you're just basically lengthening the carbon chain. And the general formula of alkanes is CnH2n plus 2. This is a formula that tells you if you have a certain number of carbons, then you'll have a certain number of hydrogens relative to the carbons. And you can see that it makes sense. For example, ethane, you've got 2 carbons, and therefore 2 times 2 plus 2 will give you 6. So C2H6 is the molecular formula of ethane, which is the second member of the series. So you can see that you're simply just increasing the carbon chain as you go throughout the series, and this is also why each of the members only differ by 1 carbon and 2 hydrogens. So let's actually go through each of these different functional groups. The first one that you'll have to know is alkanes, which again are hydrocarbons with the same general formula that I showed you before, CnH2n plus 2, and you do need to memorize this. And so remember I said that the functional group of alkanes are that they only have carbon-carbon single bonds, and so they're also hydrocarbons as well. So basically, because they are all single bonds, no more atoms can actually add on to the molecules, and so they are described as saturated hydrocarbons. And one really quick important thing that I should say is in organic chemistry, because you're mainly dealing with the carbon chains, you need to be able to understand that if you have a carbon chain like this, each carbon can hold a maximum of 4 single bonds, or 4 bonds in total. So generally they're going to be, let's just take a look at this molecule propane. Whenever you're drawing a molecule, you need to make sure that each carbon has 4 bonds to it. It can't have any less, it can't have any more, it can only have 4 bonds. And so if you take a look at the single bonds, you can see the first carbon has 4 bonds, the second carbon has 4 bonds, and the third carbon has 4 bonds, right? So 1, 2, 3, 4, 1, 2, 3, 4, and so on. But if you say draw a molecule and it looks something like this, right? Then you know that something's wrong because this carbon here only has 3 bonds. So you know you're missing a bond. So you know you should actually draw one and fill it in with the hydrogen if required. You also might get molecules like a carboxylic acid, which has the functional group of carbon, oxygen double bond, and an alcohol. And this is the functional group. And even here, this carbon, you can see that it's got 4 bonds. You've got 1, 2, 3, 4. Of course, the double bond has 2 single bonds, so there's 4 bonds in total. So everything makes sense. So whenever you're drawing a molecule or organic molecule, just make sure, triple check that each carbon that you have drawn has 4 bonds, because it can't have any more, it can't have any less. Now, so with that in mind, because alkanes only have single bonds, they don't have any extra space for carbon bonds to make extra bonds with other molecules, so they're described as saturated hydrocarbons. And so generally they're unreactive because of that saturation, but the 2 main things that they undergo would be combustion and chlorination, and we will go through that. But again, the alkane functional group, the name will always end with the name ane. So here is the homologous series of alkanes that we talked about before. And so the reactions of alkanes would be combustion, which is basically burning the molecule in air, right? And so it's simply just a reaction between the organic molecule and oxygen, which is in the air. And the complete combustion of alkane, which is when there's sufficient oxygen to react with all of the hydrocarbon, and will give you carbon dioxide and water. As the examples show here. Now, the incomplete combustion of alkane is when there is insufficient oxygen, so there isn't enough oxygen to react with all of the organic or the alkanes. And so what happens then is, instead of getting carbon dioxide, you'll get carbon monoxide and water. So combustion is a pretty simple sort of equation to learn. The other one is substitution, and alkanes can react with chlorine in bright light or UV light to give a mixture of chloroalkanes. And so one hydrogen is substituted by one chlorine atom in the process, and if you have enough chlorine molecules present, then you can continue the reaction, and more of the hydrogens in the molecule will actually be sort of substituted as well. And this is easiest explained when I draw the molecule out. So these are basically the set of reactions that will be happening as we go down, but to sort of diagrammatically represent this, you've got a molecule of methane, and methane is methane. It's an alkane because it's only got single bonds attached to the carbons, and it's also an hydrocarbon. And so if you react that with chlorine in the presence of light, what will happen is the chlorine from or the chlorine atom from the chlorine molecule will actually come and displace or replace one of the hydrogens. So there's a substitution going on. So these basically swap places. And so what then you get is chloromethane, which is methane with one chlorine that has replaced the hydrogen, and HCl in the process. Now again, you can actually continue this reaction. So if you have another set of chlorine molecules, these two can actually substitute, and you can end up getting a dichloromethane, suggesting that there's two chlorine molecules in the two chlorine atoms in the molecule now, right? And that can continue on until you can actually even replace these two hydrogens, so you get one carbon bonded to 4 chlorine atoms, which would be tetrachloromethane. But it's a fairly simple sort of idea there. The next thing we're going to be looking at is alkenes, and alkenes are fairly similar to alkanes. They are also hydrocarbons, meaning they only contain carbon and hydrogen. So if you have a molecule that only has carbon and hydrogen in it, then you know that it's either going to be an alkane or an alkene. Of course, the differentiating factor is that alkanes only contain single bonds, and alkenes actually have the functional group carbon-carbon double bond. And so therefore it has a general formula of CnH2n. It simply has 2 times more hydrogens all the time than carbons. And so because they have these carbon-carbon double bonds, they can undergo addition reactions, right? And therefore they're called unsaturated hydrocarbons. Remember, carbons can have up to 4 bonds to them. So if we take a look over here, this is a molecule of ethene. It's an alkene because you see that it's a hydrocarbon and it has a carbon-carbon double bond. Now imagine you were to break apart this middle double bond here, right? So you just simply break it into a single bond. What that means is each of these 2 carbons only have 3 bonds now. Remember, carbon must have 4 bonds. So that means there's one more room for a molecule to jump in and get added to the ends over here. And so these are what most of the reactions that we'll talk about regarding alkenes will be, which is simply addition reactions. Molecules just add onto the molecule by breaking apart the carbon-carbon double bond. The first thing we're going to be looking at, this is the homologous series of alkenes. We got ethene. It starts from ethene because you can't have a carbon-carbon double bond, which is the functional group of alkenes, without having 2 carbons to begin with. So ethene is the first member of the series here, and you just increase the length of the carbon chain by 1 as you go down the list. But yeah, so actually I think what we'll start by doing is looking at the manufacture of alkenes. right? So alkenes are made by cracking alkanes. So the large alkane molecules obtained by fractional distillation of petroleum are actually passed over heated catalysts such as silicon oxide or aluminium oxide, and these larger alkanes are broken down into simpler alkanes, alkenes, and maybe even hydrogen. So there's various things that could happen, but so the first scenario is that the alkane breaks apart into an alkane and an alkene, right? And so in this example here, decane, which has 10 carbons and 22 hydrogen, it breaks apart into octane and ethane. Of course, octane is an alkane. It has the general formula CnH2n plus 2, whereas this is obviously an alkene with the general formula, if it has 2 carbons, CnH2n, so 2 times more hydrogens than carbons. So if you look at a molecule and you just sort of figure out what general formula it falls under, then you can distinguish whether it's an alkane or an alkene. But either way, you can either have this scenario here where you get an alkane and an alkene forming, and this is non-specific, right? You don't always get octane and ethane. You can get other things as well. For example, in the second example, you have the same molecule decane, but you can actually split that into this alkane and this alkene, so it's different from the first scenario. But the idea is, if you add everything up, you should still get the same number of carbons and hydrogens that you find in decane. So 7 carbons here, 3 carbons here, so 7 plus 3 is 10, that makes sense, and 16 plus 6 is 22. As long as that's all adding up, then it doesn't really matter. The other situation is that you might form 2 alkene molecules of varying carbon chains along with hydrogen. And so the same alkane here, decane, will be broken apart into this alkene, another alkene, and remaining hydrogen as hydrogen gas. So there are 3 scenarios here that can potentially happen when you crack alkanes to make alkenes. So again, when we look at the reactions of alkenes, most of them will be addition reactions, and there are 3 main molecules that can add onto alkenes. It will be bromine, hydrogen, and steam, which will be the ones that we'll be looking at. So the first one would be bromine, and bromine has aqueous bromine basically has a brownish orange color. And so what happens is, if you have some sort of alkene which has the double bond, and this is ethane or ethylene, which is just basically another word to say ethane, bromine molecule will come along and actually break apart the double bond of carbon and add onto it. Remember, once you break the carbon-carbon double bond, each carbon has one more bond to for other molecules to attach onto, or other atoms to attach onto. In this case, the bromine molecules will attach onto each carbon respectively. And so what you're getting is this molecule here, which is dibromoethane, and in the process you get the disappearance of bromine, which has a brownish color. So over time, as the reaction happens, the brownish color of bromine will actually turn colorless, and that is a test for alkenes. It suggests that there are alkenes present because the reaction is happening. So if you want to test for the presence of alkenes, basically you need to add bromine to it, and if it turns colorless, then you know some sort of reaction is happening, and the reaction would be the reaction with some sort of alkene, suggesting that that is a positive test, suggesting that there is indeed an alkene somewhere in the substance that you added the bromine to. So that's a good test for alkenes, and you do need to know that. The other addition reaction would be with hydrogen. And so hydrogen reacts with alkenes to produce alkanes. Remember, because alkanes are simply hydrocarbons that have carbon-carbon single bonds, and they're all attached to hydrogens with single bonds as well. So if you were to break apart an alkene, like ethene here, and you were to add hydrogen to each of these respective carbons and break apart the carbon-carbon double bond, you'll simply just get an alkane. And so you get an ethene, and you add the hydrogen to it, and you'll get ethane in the process. There are certain conditions that are required for this reaction to work, though. The temperature must be around 150 degrees, and you need a nickel catalyst. And so these conditions are really important, and you need to know each of the conditions if required for each of the different reactions. The last one is the addition of water, and water can react with alkenes to make alcohols. This type of reaction is called hydration simply because you're adding water to something. The conditions required for this reaction would be a temperature of around 300 degrees, a pressure of around 60 atmospheres, and phosphoric acid catalyst. And so what you get would be ethylene, or ethane again, and you've got water, and what actually happens, of course, is the carbon-carbon double bond breaks apart, and you have the water breaking apart into the OH group and the H group, and each of them add on to the carbon respectively. So if I were to sort of draw that out, water, of course, is oxygen attached to two hydrogens. The water will sort of break apart here, so you get H and OH, and the H will go over here, and the OH will go over here, and so therefore you must of course break the double bond of the carbons there, allowing for the extra bonds to occur, and so therefore you get this molecule here in the process. And because it now has the OH functional group attached to the carbon, then that is indeed an ethanol, or an alcohol, and we will be going through alcohols in the next few slides. But of course, the idea is that alkenes undergo addition reactions, and the three main molecules of addition that you need to know would be, as I said, bromine, hydrogen, and water, and bromine is a fairly good test to dictate the presence of alkenes, simply because of the color change that it comes with it. So, talking about addition, polymerization is the formation of a long chain of molecules called polymers from a large number of smaller molecules. So, ethene, of course, has a structure here, and what you can do is actually break apart the carbon-carbon double bond, just like we did with the others, and this unit can actually join with another unit. And so, if I were to draw it out, right, if you have the ethene molecule, if you break apart this double bond, then you have room for two more carbons, just like normal addition. But this unit, this entire unit, can actually add on to it. So for example, like this, and this is another ethene molecule that is just breaking apart its double bond, and you can see that this unit can be repeated over multiple times by just simply breaking apart the double bond and adding one unit onto the other. And so what you get is this molecule, or this unit, repeating itself over and over and over and over again. And so therefore you would denote that in this sort of format here, where you just put a square bracket around the unit and you just chuck down the letter N down below, suggesting that there's multiple units of this single unit in the polymer, which is basically the long chain that is formed from these individual units. So the third thing that we're going to be looking at is alcohols, and so the alcohols have a general formula of CnH2n plus 1 OH, and OH is of course the functional group that you find in alcohols, and they all end with the name ol. And if you look at the homologous series, it starts with methanol with one carbon, and it gradually lengthens into 2 carbon chains, 3 carbon chains, into ethanol, propanol, and butanol along the way. But of course they all have the same functional group of OH groups attached to one of the carbons. And so if you take a look at the ethanol manufacture, ethanol can be manufactured by two main methods: the catalytic hydration of ethane and fermentation. We looked at the hydration of ethane when we took a look at alkenes. And so if we were to revise that, of course, you've got the carbon-carbon double bond in ethene, and you would simply add water to that under the conditions of 300 degrees, 60 atmospheres, and phosphoric acid catalysts, and you would therefore create the OH functional group attached onto the carbon as a result. And so that would form the molecule ethanol. And so the advantages of manufacturing ethanol this way would be that there are no waste products and ethanol production occurs continuously. The disadvantages would be the use of crude oil, which is non-renewable and requires a lot of energy for the maintenance of these conditions here, high temperatures and high pressures. The other way you can do it is fermentation, and fermentation is the chemical breakdown of glucose by yeast or sort of any other microorganisms. And so glucose is broken down and you form ethanol and carbon dioxide in the process. Carbon dioxide and ethanol or the products here. The entire reaction is catalyzed by the yeast enzymes, which are basically biological catalysts. And so the advantages would be that it's renewable and you're using less energy because less temperatures and pressures are required for this compared to the catalytic hydration of ethane. But the disadvantages would be that they're slower in production. It's a batch process, meaning that you need a new sort of batch of yeast once the yeast die, and it produces carbon dioxide, which is theoretically a waste. But yeah, there are two main methods of making ethanol, and Cambridge wants you to be aware of that, along with its relative advantages and disadvantages. So the properties of ethanol would be that they burn in blue flame, and the combustion of ethanol will give you carbon dioxide and water, just like the combustion of alkanes. Ethanol can be used as a fuel, as a solvent in perfume and food industries, and some cultures and alcoholic drinks, and to make other organic chemicals such as esters. And so the next thing that we're going to be looking at is carboxylic acids. And carboxylic acids have the general formula of CnH2n plus 1 with the COOH functional group. It ends with the name oic acid. And so if you take a look over here, these are the homologous series of carboxylic acids, and you can see the lengthening chain as we go down through the members. But the idea is that ethanoic acid manufacture can happen by, one, the oxidation of ethanol by fermentation. So the Acetobacter can oxidize or ferment ethanol into ethanoic acid. So it's a simple equation. You have ethanol, you add that to oxygen, and in the presence of bacteria, you get the ethanoic acid and water. And this is of course ethanoic acid because it's got two carbons in the carbon chain. Oxidation of ethanol can also happen by the acidified potassium manganate, which is an oxidizing agent. So when ethanol is heated with an oxidizing agent such as acidified potassium manganate, you get ethanoic acid being formed in the process, like this equation over here. So you've got the ethanol getting added to the oxygen, which is the process of oxidation, and you get ethanoic acid. If I were to draw that out, it would look, ethanoic acid would look like this. So please don't get confused when you see the OH group and immediately associate that with alcohols. If it's this entire thing is the functional group, and that's indeed carboxylic acid. So if the carbon is bonded with a double bond with the oxygen and also has the OH bond attached to it as well. So moving on, the properties of ethanoic acid would be that because it's an acid, all carboxylic acids, of course including ethanoic acid, is a weak acid. This means that they demonstrate typical acid properties, and they only partially ionize an aqueous solution, which is what weak acids are. And so the general reactions with of properties of acids would be they have the classic metal plus acid reactions, giving you salt and hydrogen, and you've got the base plus acid and the carbonate plus acid reactions that you need to know of. The only real thing here is it's exactly the same as you do a normal acid plus sort of metal reaction. For example, if you have magnesium added with ethanoic acid, you'll actually get magnesium ethanoate as the salt. And so if you're sort of confused about how the ethanoic acid makes or ionizes, basically you have the ethanoic acid being like this, and you get the ionization of one hydrogen, which is of course the properties of acids. It makes hydrogen ions, along with this structure here. And so if you know that, then if you're adding that to magnesium, it's simply magnesium ions combining with the ethanoate ions. And so if you of course change the oxidation states around, you'll find you get MgCH3COO, and you put that in brackets 2. And just like how you just formulate any sort of other chemical formula. Okay, so moving on, carboxylic acids and alcohols, if they react with each other, you can form ester. And the conditions required for this reaction is heat and concentrated sulfuric acid. So if you have any sort of carboxylic acid like so, you'll have the functional group COOH. And if you can actually react that with an alcohol, because the OH group of the carboxylic acid will actually react with one of the hydrogens on the OH group of the ethanol, and what do you get? You get water, because you got H2 and O. And so these groups of atoms leaves as water, and you get a direct link happening between the carbon and the oxygen. So the carbon from the acid and the oxygen from the ethanol or the alcohol, whatever alcohol it is. In this case, it's ethanol. And so you get this structure here, and this part, or the carbon-oxygen bond that you get, is called the ester link. And this is an ester. And esters are always named something io something O8. And if you take a look at this structure, the alcohol part of the ester always comes first. And in the alcohol part, you know it's got 2 carbons, so it's eth. So it's ethyl, and the carboxylic part comes second, which is also 2 carbons, so it's eth as well. So this is ethyl, ethanol. Sorry, actually, I'm just gonna. Oh, sorry. Yes, no. In fact, I miscalculated that. So the alcohol part is still correct as ethyl because it's got 2 carbons, but I didn't see the last carbon there. So it's, here we go, 3, 1, 2, 3 carbons. So it's propanoate. Ethyl. So something al something o propanoate. Right, and so the only really counterintuitive thing is that when you name esters, the alcohol part, which is seemingly the last part of the ester, actually comes first. So ethyl propanoate in this case. If this had 2 carbons, then it'd be eth. So ethanoate. If it had 5, that's bute. So butanoate, and so forth. Right, so polymers are large molecules built from smaller units. Different polymers are built from different monomers and have varying linkages between the monomers. So there are 2 main methods of polymerization. There's addition and there's condensation. We took a look at addition before, so we're going to be taking a look at condensation, in which in a condensation reaction, 2 monomers react together and join. And during the reaction, a molecule or water molecule, is lost in the process, and therefore we call that condensation. If we were to add something, we would call that hydration. If we were to add water to break something down, we call that hydrolysis, but we will be going through that in a bit more detail later. All the synthetic and natural polymers that we will be looking at in this course are forms of condensation polymerization. You've got nylon, you've got terylene being synthetic polymers, and we've got proteins and carbohydrates being natural polymers. So the synthetic polymers are mainly polyamides or nylon that you need to know. So the 2 monomers that you find in these are the dicarboxylic acids, which is a certain group of molecules which you would sort of label as just a box of some sort with 2 carboxylic functional groups added onto each side, like over here. And you've got the diamine, which is it's got a block of molecules which you don't need to know, you just put it as a block, like so. and it's got two NH2 groups attached on either side. We call that a diamine. And so these two monomers join together, and so the OH group of the carboxylic acid will react with an H from the NH2 group over here, and so you get a direct link between the carbon and the nitrogen, and this is called the amide link. This is sort of similar to what happens in an ester, remember? Except in an ester it was an OH group, and the H of the OH reacts with the OH of the carboxylic acid. But either way, the hydrogen from the nitrogen group here reacts with the OH group in the carboxylic group, and you get a direct link formed between carbon and nitrogen, and that's an amide link. And if you were to sort of continue on that chain, you would get a series of molecules like this, and that is the official sort of diagram that is listed in your syllabus. Polyesters or tetraline, the two monomers are again dicarboxylic acids or diacids, the same sort of monomer, except the second one is a diol. So this is exactly sort of similar to an ester, and in fact it is. It's an ester link where the OH group of the carboxylic acid reacts with the H from the OH group from the alcohol, and so if you join those two together, again you get the direct link between the carbon and the oxygen, and so you get the ester link happening there, and you also get hydrogen being removed, because again these molecules here make hydrogen, and that's being removed to form the bond there. So if you were to sort of chain that up, you'll get a molecule that looks like this to the right. The natural polymers consist of proteins, which are built from amino acids, and monomers that are joined via amide links through condensation polymerization, exactly like we looked at before. It's just different units. So basically, we've got the carboxylic acid group, and you've also got the amine group. So the amino acids will basically have the carboxylic acid group and the amine group as well, attached onto the molecule. So if you were to, again, similar thing, the OH group from the carboxylic acid will join or will form water with the hydrogen group from the amine group that you find in the amino acids, and so in the process of condensation, removing that that water will bond the carbon and the nitrogen, and you get a peptide or an amine link forming. You can actually reverse the process by adding water to break down the formed polymer back into its simplified amino acids or monomers. And so that here is just demonstrating that. You can actually hydrolyze it by boiling it with hydrochloric acid to make it back into amino acids. The last thing is carbohydrates, which is complex carbohydrates. Polysaccharides are made from larger number of simple sugar units that are joined through condensation polymerization. So in sugars you have the sugar monomers, which are basically sort of diols with two hydroxyl or alcohol groups. And so if you were to simply use the same process, the OH group will just join with the H group from the other OH group, and so if you form these, you get water happening, and you remove the water, that's condensation. And so you can join everything together, and you'd form a large chain of these sugars. And so this is actually wrong. I'm just going to remove that. But again, you can actually hydrolyze it back as well. So condensation is removing water to join everything up to make larger compounds, but the polysaccharides, which is the larger compound, you can convert that back into simple sugars by hydrolysis. And this reaction can be catalyzed by enzymes or heating with dilute hydrochloric acid as well. So structural isomerism, we talked about this in the prior sort of slides, but basically they're the same molecule that have the same molecular formula, but they have different structures, and that's much to do with how the carbons are attached. You can see that in this molecule here, butane, it's a single chain, but isobutane, which is a structural isomer of this molecule here, is different because the carbons attach differently. And same with these ones here. So thank you for watching, guys. It is a long video, but I will timestamp all the individual topics. Please join Patreon for exclusive past paper tutorials and more. Please like, share, and subscribe because it really helps this channel, and I hope to see you in the next video. Cheers.